So, um, yeah, so let me near the open panel. So, yeah, can you see the screen? Logosri, can you see the screen? Hope you can see the screen. If not, let me know. Okay. So, one second. Okay. So, firstly, suppose summation even be a series of positive and negative real numbers. And assume even dash is equal to mod even. Then obviously summation un prime is a series of positive summation even is a series of positive real numbers. Okay. And the thing is, if this if this summation of this mod even convergent, then we say that this series summation even is convergent absolutely. Convergent absolutely means, so what does mean convergent absolutely? If un is said to be summation even should be converges absolutely if the summation mod even converges. Okay. And there is a well-known theorem just for the record. Let me state this. This tells that absolutely convergent implies convergent. Okay. So this is one way of the showing a series having both positive and negative terms convergent. If you can show that the series is absolutely convergent, then this gives that the series is absolutely convergent. Okay. So for example, consider the series 1 minus half square plus 1/3 square plus 1 by 4 square minus 1 by 5 square minus 1 by 6 square plus dot dot dot. Now this series is absolute. This is convergent. Why? Because it is absolutely convergent. Okay. So there is also another example, that is 1 minus half square plus 1/3 square minus 1/4 square plus 1 by 5 square minus 1 by this series. Now this is also convergent as it is absolutely convergent. This series is absolutely convergent. Obviously. So consider the next example, that is, so consider a third example. Fix any x belongs to x, and then summation, the consider the series summation sine nx by n square. Now this series is absolutely convergent since mod sine nx by n square less than equal to 1 square, and comparison, and since this summation 1 is convergent, so by comparison test summation mod sin x by n square, this converge. Okay, so these are the three examples. Loshir, do you understand this? If you have confusion, please let me know. Okay, so well, I will wait for 1 minute. If you have any confusion in the definition or the examples, please let me know, or else then I'll continue. Okay. Okay, so it seems that there is no issue, there is confusion. Okay, so let's go to the next 17. Now there is a one theorem, but just for the sake of record, let me state it. The theorem tells that suppose if summation un be absolutely convergent, and Vn be a bounded sequence, then the series summation un Vn is absolutely convergent. So, as in some examples, actually these are the application of the previous theorem. So some examples are the following. So first example, consider the series this 2 by 1 cube minus 3 by 2 plus 4 by 3 minus 5 by 4 cube plus dot dot dot. Suppose let this series be un. Then observe that un is nothing but there is n is equal to nothing minus 1 to the power n plus 1 into n plus 1 by n cube. This is what? This is equal to minus 1 to the power n plus 1 by n square into 1 plus 1 by n. Okay, and we can write it as n, where n is the minus 1 to the power n plus 1 by n square, and n is equal to 1 plus 1 by 1. So then, yeah. Now observe that the series summation n converges absolutely, and the series bn is bounded. So summation a and bn, so the series summation a and bn is absolutely convergent. Well, so now there is some similar thing. There is the same thing. There was a ratio test. Just for yeah. So first, let me start this test. Then I mean we'll see some examples of it. So let summation even be the series of arbitrators, and let limit mod un plus 1 un is equal to 1. Then ratio test tells this summation even converges absolutely if this L is less than 1 and this series divergent if small is greater than equal to. Okay, so sorry, it is not equal to, it is exactly greater than 1. Okay, so well before giving example, there is another similar test uh, which is known as the root test. This is what this gives. Let summation un let summation un be a series of arbitrators, and let limit mod un to the power 1 by n is equal to small l. Then summation un is convergent absolutely if L is less than 1 and this summation even divergent if L is greater than. Okay, so there's the statement. So now let's see some examples of this. So first problem, examine the convergence of the series 1 minus 2 square factorial 3 plus 3 cube of factorial 3 minus 4 to the 4 factorial 4 plus dot dot dot. Yeah. So using root test or ratio test, examine the convergence of this series. So first you try. So I will wait for some minutes. Then if not done by you, then I will tell how to solve this problem using this ratio test or root test. Okay. First you try. Okay. I shall wait for 2 minutes. If anybody can solve it, please let me know. Okay, so has anybody solved it? Okay, so let me solve it. Okay, so let denote this summation event. So the nth term is equal to minus 1 to the power n plus 1 n to the power n factorial n. Okay. Now observe that the un plus 1 by mod un. This is what this n plus 1 to the power n plus 1 by n plus 1 into 1 by n to the power n. This is equal to n plus 1 by n whole to the power n, and this limit mod un plus 1 by un which is greater than 1. So by ratio test the series summation un divergent. Okay. So yeah. So let me repeat this solution again. So first, so before let me show you that ratio test statement. So what does the ratio test tells? It tells that if the limiting value, this is small l, if this limiting value is a, and if l is less than one, then the series is absolutely convergent, and if l is greater than one, then it's divergent. Okay. Now consider this example. Now first we write denote this series summation when, and we write minus 1 to the n plus 1 into the factorial. Then we are calculating mod un plus 1 by un. Now we are now we see that this is equal to 1 plus 1 by whole to the power, and limit of this is greater than 1. So by ratio test, this series summation un is divergent. Okay. Yeah. So this is one example. So consider the second example. Examine the convergence in the following. Minus 2 factorial divided by 4 plus 3 factorial is squared by 6 factorial is 4 factorial minus dot dot dot. So first you will try. I shall wait for some minutes. If you log studio is there only. So log studio first try it. If you cannot solve, let me know. Or if you can solve it, then also let me know. Okay. Okay, so let me tell how to solve this. Okay. So first, as usual, so let's note the summation even, what the inner term even is, minus 1 to the power n plus 1 n factorial whole square by 2n whole factorial for all n greater than equal to 2. Now consider this thing. In modulus, this what this is equal to limit n plus 1 whole square into 2n plus 1 into 2n plus 2 is equal to 1 by 4, which is less than. So by ratio test, this series summation is absolutely convergent. So let me repeat. So we are putting even is minus 1 to the n plus 1 n factorial by n factorial whole square to n, and limit of mod un plus 1 by even, which is 1 to less than a 1. So ratio test gives the summation even absolutely convergent because the ratio test, this is less than 1, then it is absolutely convergent. That's way okay. So now there is some another thing known as the alternating series. So alternating series is what? If so let so if even is greater than for all n, then the series summation 1 to infinity minus 1 to the power un plus 1 un called alternating series. So there is one test, namely the Leibniz test. L-E-I. Sorry, my spelling mistake. So the Leibniz test is what? This Leibniz test actually talks about the converting the alternating series. So this tells that if when we are monotone increasing sequence of positive real numbers, and if limit even equal to 0, then the alternating series u1 minus u2 plus u3 minus u4 is convergent. So this is the main. So using the Leibniz test, so do the show the following cell convergent. Examine the convergence of the following series. So the series is 1 minus half plus 1/3 minus 1 for plus. So, what is the nth term? The nth term is minus 1 to the power n plus 1 by 1 plus n. So here un is equal to 1 by n. This is monotone decreasing. So by Leibniz test, n minus 1 to the power n plus 1 by 1 plus n convergent. Okay. So and also observe that if we take the consider the modes, that is 1 half 1/3 plus dot dot dot, this is divergent. So convergent does not imply absolutely convergent. So convergent does not implies absolutely convergent. Okay. So the next, consider the series. Examine the convergence. One by one plus a square minus one by two plus a square, one plus three by a square. Now this is what this series. You will discuss. We need to show this convergence. So this series is general term is minus one to the n plus one by one plus n by a square. So this un is equal to what? 1 by n plus a square, and which is, so the sequence un monotone decreasing. And also observe that the Leibniz test we also need to ensure that the limit even is 0. So here, what is the limit of 1 by n plus 1 square? 0. So I list it. This series. Okay. Now consider the series 1 minus half plus this. So what is the nth term is there? I mean the nth term is 1, 3, 5, 2n minus 1, 2, 4, 6, 12. This is the nth term. Okay. And this is nothing but the un. Now first, well, so since we had, now we need to show the convergence using the Leibniz test. Okay. So we need to show summation even. We need to show un is decreasing and limit un is equal to 0. Well, limit un is 0, that is, I mean, well, I mean, un is decreasing, that is okay, but how to show that limit un is 0? So, Lagashari, can you please try? So, I will wait for some minutes. If you can solve it, let me know, please. So, show that this limit un is 0. Okay, so let me tell how to do. So now, so consider un plus 1. This is what? This is 1, 3, 5, 2n minus 1, and 2n plus 1 by 2, 4, 6, 2n into 2n plus 2. So what is the un plus 1 by un? This is equal to what? This will be equal to 2n plus 1 by 2n plus. And the remaining value is 1. Sorry, this remaining value is 1. Okay. So, so this limit un is equal to 0. And so by Leibniz test, that series convergent. Okay. So this is the these are some examples applications of Leibniz test. So now there are sorry. Well, so now there are two important tests, namely Abel's test and Dirichlet's test. So first, let me start the Abel's test. Well, so Lagashri, so till now what has been done? Let me know. Do you have any confusion? So I'll wait for 5 minutes. I'll start the Abel's test after 5 minutes. So till then you go through the things that we have done and let me know if you have any confusion. Okay. So I will start after 5 minutes. Okay, so logically, do you have any confusion or doubt? Okay, so I think everything so the clear. So well, so let's start with the apples test. This tells this test tells that if the sequence Bn is monotone bounded, its summation a n and convergent series, then summation a n bn is convergent. Okay. So consider the following example, that is the test the convergence. Examine the convergence. The series is 2 to infinity minus 1 to the power n plus 1 into 1 by n log n. So logically, can you please try the examine? Can you please try the converge of the series using the Abel test? I shall wait for a couple of minutes. You please try, and if you can ever solve it, please let me know. Okay. Okay. So say okay. So how to find examine how to get the convert this in the Abel test? So consider the series now. Observe that summation minus 1 to the power n plus 1 by n is convergent. and the sequence 1 by log n from n equal to 2 to infinity is monotone decreasing and bounded. So by Abel's test, this is convergent. By Abel's test. Okay. Now, consider second example. Examine the convergence. Summation 1 to infinity minus 1 to the power n plus 1 into n to the power n by n plus 1 to the power n plus 1 by Abel's test. So we should try this convergence of the series using Abel's test. I shall wait for a couple of minutes, so you please try. Okay, so let me solve it. So now observe that this series summation minus 1 to the plus 1 plus 1 is convergent. And the sequence 1 plus 1 by n to the power minus n monotone modern decreasing and bounded below. So by Abel's test, the above series converges. So, so in the Abel's test, first I will go through again this Abel's test. So, what does this test tells? It tells that if we have a sequence Pn, which is monotone bounded sequence, and if this series summation n is convergent, then summation n is convergent. So then we have discussed two examples. First one is summation 2 to infinity minus 1 to the power n plus 1 by 1 plus n log n. Here first we have observed that this summation minus 1 to the power n plus 1 by n is convergent, and we observe that the sequence 1 by log n inverted to infinity is more or not equal to the bounded below. So this thing is convergent by Abel's test. And for the second example, the series of summation 1 to infinity minus 1 to the power n plus 1 by n to the power n by n to the power n by n plus 1 to the power n plus 1. So first by Abel's test, this summation minus 1 to the n plus 1 by, I mean, this is convergent by Leibniz test. This is an Abel, sorry. And the sequence 1 plus 1 minus hold to the minus the more or decreasing plus bounded below. So by Abel's test, the above series convergence. Okay. So Lagishay, please go through this Abel's test once again. Let me know if we have a confusion. If not, then we shall dive into Drake test. Okay. So I shall wait for a couple of minutes, and please let me know do you have a confusion in the Abel's test or any portion before that. Okay. Okay. So let's okay. So let's go with the drift test. Okay. So this test is what? So test tells that if the sequence n is monotone, converging to 0, and the sequence of partial sums Sn is summation when bounded, then the series summation NBN is convergent. Okay. So this is the statement reach test. This test if for the sequence Bn is not converging to 0 and the sequence of partial Sn of the series summation is bounded, then the series summation is convergent, right? So this is and other one thing that Leibniz test is a particular case of Dirichlet's test. How? Because if Bn monotone decreasing and converging to 0, then the series summation minus 1 to the n plus 1 Bn is convergent by Dirichlet's test. As the sequence of partial sums Sn of the series summation minus 1 to the n plus 1 is bounded. So this Leibniz test is another from Dirichlet's test. Okay. So now, yeah. So let's consider some examples. Examples of, let's examine the conversion of sequences in Dirichlet's test. Examine the convergence so Logeshri, please try this. Try it out for a couple of minutes. I shall wait. If you can solve it, please let me know. So okay, so so observe that this series, I mean this sequence 1 by n is converges 0 and this is monotone decreasing. So by Leibniz test, this I of series summation 1 to minus 2 n plus 1 by 10 is convergent, okay? Now consider this. Now examine the convergent series summation 1 n minus 1 to the power n plus 1 by log n plus 1. So how do this? So observe that this log n plus 1, this series 1 by this log n plus 1, it is more decreasing and this converges. Even series converge. Leibniz test. Okay. And Leibniz use Leibniz test and use Dirichlet test and almost set. Okay. So yeah. So I shall go through the Dirichlet test, instrument and those examples again. Okay. So what does the different test? This tells that if we have the sequence, so if you consider the sequence Bn, which is monotone converging to 0, and sequence the partial sums Sn of the series summation n is, I mean, then the series summation n Bn is convergent. Okay. So yeah. So and next thing we have showed that the Leibniz test is nothing but a Dirichlet test. When Leibniz is a special case of Dirichlet test. How? So consider the Bn is a monotone decreasing and converges to 0. Then consider the series summation minus 1 to the power n plus 1 Bn. This is converging to Dirichlet test as the sequence of partial sum Sn of summation minus 1 to the n plus 1, which is bounded. So first example is the examine the convergence of this series 1 to infinity minus 1 plus 1 root n. So I mean these are actually direct application of the Leibniz test. So why? Because for this series 1 by root n, 1 by 0, which is more decreasing. So the Leibniz test, the alternate series is converging. And similarly, the last one, minus 1 to the power n plus 1 by log n plus 1. This 1 by log n plus 1 is more decreasing and converging to 0. So the Leibniz test is convergent. Okay. So, Loshri, you just go through the Dirichlet test again. I shall wait for 5 minutes. If you have a confusion, please let me know. Else, we can continue with the conditionally convergent series. Okay. So I shall wait for 5 minutes. You shall please go through that Dirichlet test. Okay. Okay, so let's start with the apples test. Sorry, let's start with the conditional convergence series. Okay. Yeah. So what is this conditional convergence series? The by definitions first. Let's go to definition. So a series summation even called conditional convergent if summation even is convergent, summation not even not convergent. Okay, this is known as a conditional convergent. Conditional convergent if the summation this summation series this summation even conditional convergent if the main given series is convergent but its absolute term series is not convergent. Okay. So for example, also there is 1 minus half plus 1 third minus 1 plus third. This is conditional convergence. Why? Because this is convergent by Leibniz test, but not absolutely convergent, which we have seen in the last live session. Okay. So yeah, so another example of conditional convergence is that this summation 1 to infinity minus 1 to the power n plus 1 by 1 by 2 n minus 1. This series is convergent by Leibniz test. But its absolute term sequence not convergent. Conditionally convergent. Okay. So now consider the third example. Series 2 to infinity minus 1 to the power n plus 1 11. Convergence. Convergent by Allen switch. This series summation 1 by log n divergent. I think you are smart enough to get the point why this summation 1 by n log n is divergent. Okay. So this series, the summation minus 1 to the power 1 plus n by n log n is absolute, is a condition conversion. Okay. So, Lois Sharik, please go through this concept of conditionally convergent once again. I shall wait for a couple of minutes, and then go with we shall go with okay. So please um, go through the concept of conditional convergences once again. Okay. Okay. So there is once again. Okay. So I think it's it's always necessary to revise the things that we have done today. Okay. So let's start from the beginning. Okay. First what have we introduced? First we have introduced the concept of absolutely convergent. So what is this? Suppose you have a series of mixed terms, that is mixed positive and negative terms, and let un prime is equal to mod un, and let summation un dash is a series of positive and negative real. Then summation un dash is a series of positive real. Now, if summation mod even is finite, then we say that is finite. Sorry, I mean to say, because summation mod even converges, then we say there is summation even converges absolutely. Okay, and then there is a theorem which tells that absolute convergence implies convergence. Okay. So, for example, consider the series 1 minus half square plus 1 third square minus plus 1 fourth square minus 1 5 square dot dot. This is convergent because this is absolutely convergent. Similarly, this second series is convergent because it is absolutely convergent. Now, for any x belongs to R, consider the series summation sin nx by n square. This is absolutely convergent because sin nx by n square less than equal to 1 by n square. And summation 1 by n square finite. If there is another theorem which tells that if summation even is absolutely convergent and Vn be bounded sequence, then the series summation even Vn is absolutely convergent. So, for example, consider this set summation even. Consider the series 2 by 1 cube minus 3 by 2 cube plus 4 by 3 cube minus 5 by 4 plus dot dot dot. Okay. Here, what is un? Un is minus 1 to the power n plus 1 into n plus 1 by n cube. This is nothing but minus 1 to the n plus 1 by n square into 1 plus 1 is n bn. So, this summation n converges. What is the n? The n is minus 1 to n plus 1 by n square. Bn is 1 plus 1 by n. This summation an converges absolutely and bn is bounded. So this summation a and bn is absolutely convergent. Okay. Now look at the ratio test. So still there is summation even with the series of arbitrator and let limit mod un plus 1 by un is 11. Then summation even converges absolutely if L less than 1. This test says that if L is less than 1, then the series converges absolutely, and if L is greater than 1, then the series is divergent. Now there is something in the root test. So the summation un with a series of arbitrary terms and let limit mod un to the power 1 by n is equal to smaller. Then summation un convergent absolutely if L less than 1, and this summation was divergent if L greater than 1. Okay. So yeah. For example, examine the convergent following series: 1 minus 2 square factorial 2 plus 3 cube of factorial 3 minus 4 cube of factorial plus dot dot. So if we call this series to be summation un, then un will be minus 1 to the power n plus 1 into n to the power n of factorial. And if you take the modulus of this, then we can clearly see this is I. So this modulus is 1. This will be 1 plus 1 by n whole to the power n. A limit mod un plus 1 by un is e, which is greater than. Show a ratio test. The series summation un is divergent. So actually, please, if you have any confusion in this, please let me know. I shall wait for a couple of minutes. Okay, I shall get back for 3 minutes. Please let me know if you have any confusion. Meanwhile, you go through this portion that we have done. Okay, I shall come back. Okay, so Toshira, I hope you don't make confusion in the previous portion. So let's continue from here. So now, then we have discussed examined of the one of the following series, namely 1 minus 2 factorial whole square of 4 factorial plus 3 factorial whole square plus 6 factorial dot 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 minus 2. And this is organic series. So in the term un is minus 1 to the power n plus 1 n factorial whole square by 2n whole factorial And this limit mod un plus 1 by un is equal to what? Is equal to limit n plus 1 whole square by 2n plus 1 into n plus 2. This is 1 by 4, which is less than 1. So a ratio test, this summation un is absolutely convergent. Now there is another thing, alternating series. Let un greater than 0 for all n. This, I mean, what is this? So, and then the series summation 1 to infinity minus 1 to the power n plus 1 un. This is called alternate. That is, it is plus minus in this form. u1 minus u2 plus minus. This type of this pattern is not the alternating sign, so this is not alternating space. The first test that it comes under the alternate is known as the Leibniz test. This tells that suppose even be a monotone decreasing sequence of positive real numbers, and if limit un is equal to 0, then the alternating series u1 minus u2 plus u3 minus u4 plus dot dot is convergent. And now we need to examine the convergence of the following series: 1 minus half plus 1/3 minus 1/4 plus dot dot. So this is minus 1 to the power n plus 1 into 1 by n. Un is un equal to 1 by n, monotone equal. So by Leibniz test, minus 1 summation of minus 1 to the n plus 1 by 1 is finite. Finally, this series is convergent. And also note that this 1/2 plus dot dot dot, this is divergence. Absolute convergent does not imply absolute convergence, and this actually gives the concept of conditional convergence that we have already seen. Well, so so this is revision. So let's go through the other discussion. So first convergence series 1 by 1 plus 1 square minus 1 by 2 plus this 2 plus a square plus 1 by 3 plus the minus dot dot dot. This series can return minus 1 to the n plus 1 into 1 by 1 by n plus a square is the nth term. And this even there is 1 by n plus a square is monotone decreasing and its limiting value is 0. So a Leibniz test minus 1 to the n plus 1 into n plus 1 square is convergent. And 1 minus half plus half dot 3 by 4 minus 1 3 5 by 2 4 6 dot dot this converge. This is actual convergence series. How? Because if you call this even, then we can show this even is more even is monotone decreasing, which is easy to observe, and limit even is 0. Why? Because if we consider this limit un plus 1 by un, this limiting value is 1. So this limit un is equal to 0. So the Leibniz test gives the alternate series convergence. So up to this, Lavish, please let me know do you have any confusion or problem. I shall wait for a couple of minutes. Please go through this once again. Please let me know do you have any confusion. Okay. And then we shall revise the rest of the portion. Okay, so I hope you are. I hope that there is confusion or there is no doubt. If you have doubt, let me know. So then let's reverse the Abel's test. This tells that if you have the sequence B1 which is monoton or bounded, and this summation n is convergent series, then summation n is convergent. For example, summation 2 to infinity minus 1 to n plus 1 by 1 by n log n. For this series, the summation minus 1 to n plus n by n log n, summation minus 1 to n plus 1 by n is convergent by the Leibniz test. And the sequence 1 by log n equal to repeat is mod or decrease bounded below. So this given sequence convergent by the Abel's test. Now this constant following series, which is alternate series, and the nth term is minus 1 divided n plus 1 and n to the power n plus n plus 1 to the power n plus 1. Because of that, this portion, that is the summation minus 1 to the n plus 1 by n plus 1 is convergent, and the sequence 1 plus 1 by n to the minus n is mono decreasing plus bounded below. So by Abel's test, this above series converges. So okay, so yeah. So this is up to Abel's test. So Lagashree, please let me know, do you have confusion any Abel's test or not within this, or any confusion before it, please let me know. Then we shall go through the request test, and then finally conditional convergence is okay. So please let me know any confusion is Abel's test. Not, I shall wait for a couple of minutes. Okay, so I think you have no confusion for the rest of the part. Okay. So now let's start the richness test. Okay. So sorry, I forgot. So the thing is, I think that you have no confusion in the rest of the part. So well, so up to I hope that up to Abel's test you have no confusion or no doubt. So let's start the richness test. Okay. So what does this test tells? It tells that if the sequence summation gives monotone converging region, that is the monotone sequence, the modern either monotone increasing or decreasing. And the sequence of partials essay of the series summation in bounded. And the summation n given convergent. Okay. Then the observe that the Leibniz test is a special case of ridiculousness. There is a special there I should mention a special case. If Bn is monotone decreasing and converges to zero, then the series minus 1 to the power n plus 1 Bn is convergent by Dirichlet's test. So the sequence of partial A set of and I mean, because we can have Dirichlet's because the partial of the series minus 1 to the n plus 1 bounded. Okay. So Leibniz test is a special case of Dirichlet's test. So consider the following examples. So examine the convergence of the series summation 1 to minus 1 to the n plus 1 by root n. This is monotone decreasing converges to 0. 1 by monotone decreasing converges 0. So by Leibniz test, summation 1 to infinity minus 1 to the power n plus 1 by root n is. So then the consider the next example. That is summation 1 to infinity minus 1 to the n plus 1 by log n plus 1. For this series, 1 by log n plus 1 monotone decrease and this limiting value is 0. And the conditional convergence. Conditional convergence what? So well, so the Dirichlet's test is over. So yeah, so Logisher, please let me know do you confusion or any doubt. I shall wait for a couple of minutes, then we shall go with the conditional convergence series revision. Okay. So please let me know. I shall wait for 2 or 3 minutes. Okay. So, so yeah. So now let's go into the conditional convergence series. So what does mean conditionally convergent? It means its absolute term sequence is not convergent, but the given series is convergent. So that's what we have written, that the summation even is called conditional convergent. Summation is convergent, but summation module is not. For example, the series 1 minus a plus 1 3 minus 1 for conditional convergent. Why? Because the series is convergent by Leibniz test. How we can apply Leibniz test? Because the series, the sequence 1 by n more decreasing, and if its limiting value is 0, so we can apply here the Leibniz test. So by Leibniz test, this 1 minus half plus 1 third minus 1 by 4 is convergent. But this is not absolutely convergent. Shown in the in previous lectures. Okay. It is known as this absolutely convergent is summation even. It is known as the harmonic series. Anyway, so yeah. So consider the example of some summation 1 to infinity minus 1 to the power n plus 1 by 1 by 2. This is convergent. But the Leibniz test, because 1 by 2 n minus 1, this is more decreasing, and limit n tending to infinity 1 by 2 n minus 1 is 0. But but its absolute term sequence is not convergent, because what's the absolute term sequence? Absolute sum is 1, 1 third, 1 fifth order. It is obviously divergent because harmonic series itself divergent. So this given series is conditionally convergent. So let's there is last example. So summation 2 to infinity minus 1 to the power n plus 1 by n log. So this is convergent by Abel's test. But this summation 1 by n log n is divergent. Why? Because 1 by n log n is greater than 1 by n. So this is divergent. So this series is conditionally convergent. Okay. So well, there is one concept. So okay, so there is one concept of removal of brackets. Well, so today not much time left. So in next class session we shall see this concept of removal of brackets, and using this we shall find some value of some series. Okay. So well, so I shall wait for 3 or 4 minutes before ending. So Lokeshwari, please go through the things that we have done today, and please let me know, do you have any confusion or any doubt anywhere? Okay. But one thing, the Abel's test and Dirichlet's test are the one of the most important thing in the Caesar arbitrators. So I suggest everybody, I mean, who will see this video on YouTube, please go through, please solve some problems in the, solve some problems of the convert test to convert this test, okay? Because else you can't you can't really remember in which sum or which problem we need to use or which test, okay? So practice these things, so in order to capture the tricks. So practice as much as you can. And the next day we'll go, and the next day we'll start with the Riemann theorem, and its and some applications. Okay, so let's stop here. So we'll meet on the next Friday. Thank you. I'm leaving the call.